Welcome to today's webinar. For those who has missed the previous part, my name is Adam.
And my name is Jerzy.
And we both work at the CodeLime. Today, we will introduce you to the so-called Ethernet VPN and how it can be used to interconnect different resources at the data center. But first, a few words about the CodeLime. The CodeLime was founded in 2011, and now we have more than 200 people on board. We are no longer a startup, that's obvious, but we try to keep its spirit, a culture of agility, innovation, and adaptability. Most of our team is located in Warsaw and Gdańsk. However, we work with clients in 6 different zones, so part of our team is also located there. With all that said, we often work with data centers that are deployed in spine and leaf fashion. That experience got us thinking, is that architecture final? Can it be improved? What can be done to speed up deployments, speed up change, and speed up things at all? Previous and today's presentation is all about that. A lot of technology will be used during this presentation and the demo. However, do not be afraid, they are not new, they are open source, they are well known. We're just connecting them all together to create something better, something newer.
Right, so let's start by revising the set of mechanisms that we have introduced during the first webinar, as this is something that we will build upon and extend today. So what we did is we used so-called IP version 6 link local addresses this allowed us to automatically assign IP addresses for the interfaces interconnecting the networking devices and also for the interfaces between the leaf switches and the servers. And this is especially important in case of large data centers with thousands of connections, thousands of servers, because this IP addressing does not have to be done manually. Now, even though we are using IP version 6 addressing, we can still achieve native IPv4 connectivity between the servers. So we've got dual stack, we can use IPv6 and we can use IPv4. Thanks to using dynamic routing protocol, thanks to using IPv6, we also get the possibility to use neighbor discovery protocol, which is also part of this standard. And thanks to it, we can automatically establish BGP sessions between, for example, our servers and the networking devices. So we do not need to manually specify the IP addresses of peers in the BGP configuration. Now, thanks to using a dynamic routing protocol, we can achieve load balancing when forwarding traffic through our data center. So if we've got multiple paths to the destination IP, these paths can be used together simultaneously to achieve better throughput. And if one of the interfaces or if one of the devices goes down, the failover will be really fast because we've introduced bidirectional forwarding detection into this topology, which allows for sub-second failovers. And the choice of BGP is very intentional here because it is a very scalable protocol. It is very flexible. It allows for route filtering, for route aggregation, which further increases scalability, especially when we have thousands of IP addresses and thousands of servers. But it is also a prerequisite to some additional features, such as Ethernet VPN. And this is something that we are going to talk about in today's webinar. So, you might know that in case of typical layer 2 communication in data center, traditionally VLANs were used. So we needed to stretch VLANs throughout the DC. However, here we are using IP fabric. And in order to provide layer 2 connectivity through an IP fabric, we are going to use so-called VXLAN tunneling. Where Ethernet VPN will allow us for easier configuration and for some additional benefits, which we'll talk about in a second. Now, this layer 2 connectivity can be used to provide connections between some IP addresses configured on physical interfaces. It might be addresses configured on some logical interfaces in Linux operating system. It might be some MAC addresses configured on containers, on virtual machines. So basically we can interconnect heterogeneous resources and provide this layer 2 connectivity between them. And at the same time, we also can provide multi-tenancy. So multi-tenancy, shortly speaking, is the ability to separate services of different customers, even if they are running on the same server, on the same operating system, and even if the services are communicating over the same physical network. We will show a working demo solution of what we are going to talk about today. And at the end of this presentation, we will have a short Q&A session. So if you have any questions during the presentation, please use the YouTube chat, and we'll try to answer these questions at the end of this webinar. So this is the agenda, and we hope that you will enjoy this presentation and that you will find it interesting.
Let's start by introducing two main actors that will play major roles in this demo and this presentation, the VXLAN and the AVPN. The VXLAN stands for Virtual Extensible LAN. It's a network virtualization technology that attempts to address the scalability problems that are associated with large deployments. It uses like VLAN encapsulation technique. It encapsulates layer 2 frame inside the UDP datagrams. VLAN endpoints which terminates VXLAN tunnel may be Ethernet virtual or physical ports, or virtual ports in Linux known as VXLAN interfaces. There is one implementation of the VXLAN with the switch on the operating system. It's an Open vSwitch. It's a fine example, but we'll concentrate on using plain bridges in the Linux operating system along with the FRR and along with the VXLAN interfaces. In Linux, the VXLAN can be configured in three ways: as a point-to-point interface with local and remote IP address to connect both sides. It can be configured as a point-to-multipoint interface with local address and remote addresses are being discovered using multicast. Also, it can be used as a point-to-multipoint interface where all other endpoints are discovered and advertised via BGP protocol or via some SDN controller. Since the solution where the AVPN and BGP protocol is the most flexible one and scale is fine to the thousands nodes, we'll use AVPN inside the FRR software in our demo and in our presentation. Now let's talk about the Ethernet VPN. The Ethernet AVPN allows you to connect groups of VXLAN and extend layer 2 resources, layer 2 bridges over layer 3 network. The AVPN is used for signaling, and for transportation we can use VXLAN or MPLS. However, to avoid building MPLS data plane and MPLS label exchange information, we'll use VXLAN that requires only a working IP fabric below. The AVPN allows us to stretch, as I said before, the layer 2 connectivity and provide segmentation and isolation, just like VLAN, but without the limitation of traditional networks, such as spanning tree. We no longer have to use it. We won't encounter layer 2 loops. There won't be active passive links, and the boom traffic will be limited to as little as possible. Also, the AVPN has some additional features, such as MAC IP advertisement or MAC mobility. So as soon as the resource will appear on the network, the rest of the nodes, the rest of the termination endpoints will be informed immediately via the BGP protocol. So there won't be information, there won't be forwarding of unknown unicast. The endpoint address will be well known. So also as soon as the endpoint will move, the MAC address will appear on a different machine, the data plane will be updated using a BGP protocol. There is also a layer 3 advertisement, just like in layer 3 VPN, but we are still using a VPN for layer 2 and layer 3, using different type prefixes. For the layer 3 information exchange, for the layer 3 routing, we use type 5 prefixes, and we can advertise /24 prefix, for example, into a different segment, different VRF to have routing. Last but not least, the BGP VPN is an open standard. It's not limited to the proprietary vendors or network equipment. It can be run on Linux, and one of the examples of the daemons that are supporting BGP VPN is the FRR, the free range routing daemon, and that daemon can be placed on the machines that are hosting virtual machines, containers, Kubernetes, or being a bare metal itself. This all will be shown during the demo.
Okay, so let's take a look at how EVPN can work in practice. Here on this example topology, we've got 3 different servers and a firewall, and we want these resources to be able to communicate at layer 2. Now, the devices, the networking devices, are configured using IP fabric. So we've got only layer 3 connectivity possible between them. So in order to provide these layer 2 connections for our servers and the firewall, we will use VXLAN tunneling, which will be configured on the Leaf1 and Leaf2 switch. What we'll also need is a BGP protocol with EVPN enabled. Thanks to it, it will automatically advertise information about the known MAC addresses that have been learned by each of the switches, and it will also advertise information how to reach these MAC addresses, meaning which VXLAN tunnel to use in order to do that. What we need to do in the configuration of Leaf devices is to associate the interfaces with specific VXLANs, with specific virtual network identifiers. So port 1 assigned to VXLAN 1 and port 2 assigned to VXLAN 2. And the same on the other device. When we have this configuration, we can see how this MAC address learning and connectivity works. So for the MAC address learning, we've got server 3, and let's assume that it needs to send traffic to firewall on interface with MAC-E. So it will create a new Ethernet frame with source MAC address C and destination MAC address E. This frame will be forwarded to Leaf2 interface, and it will arrive on port 1. And Leaf2 will perform standard Ethernet switch learning, so it will take a look at the incoming frame and it will write it down in the switching table. It will write down the source MAC address, and it will write down the interface through which this MAC address is reachable. Now, before forwarding this frame to the destination, EVPN will also take a look at the switching table, and it will notice, all right, I've got a new MAC address C. I need to advertise it to all other BGP peers that are also running EVPN. So it will take this MAC address and, in our case, advertise it to Leaf1. In case of large data center, this MAC address will be advertised to hundreds, sometimes thousands of devices that are also running EVPN. Okay, and Leaf1, upon receiving this advertisement, will take a look at it, and it will see I've got a new MAC address C, which will be put into the switching table, and the next copy interface in the direction of the destination will be a logical VXLAN 1 tunnel interface that leads to Leaf2. Okay, so this is the way that new MAC addresses are advertised throughout the data center. Now for the forwarding of traffic through the VXLAN tunnels. Let's say server 1 needs to communicate with server 3. So again, a new Ethernet frame is created, source MAC address A and destination MAC address C. And this frame is forwarded to Leaf1 switch. It will take a look at the switching table, and it will see I need to forward packet to MAC address C, so it needs to be encapsulated within VXLAN 1 tunnel and forwarded to Leaf2. So as an IP packet with UDP and VXLAN headers, it is forwarded to Leaf2 switch, where it is de-encapsulated. So the original frame is taken out of the VXLAN header, and Leaf2 switch will check the destination MAC of this Ethernet frame, again using switching table. So we've got MAC address C reachable through port 1, So this is exactly through which we interface. The original frame will be forwarded to the server 3. So this concept is actually quite simple when it comes to what we've seen on this slide. However, the capabilities that it gives us are actually quite far-reaching, and this is what we want to show you on the following examples. All right, so before we've mentioned that the VXLAN tunneling and the EVPN can also be run in software, so not only on the networking devices, but also, for example, on the Linux operating system. In our case, in order to do that, we are using FRR because it supports data plane integration, meaning that it can manipulate Linux's bridge tables and routing tables. Now, let's take a look for a moment at server 3. And we can see here that server 3 has one physical interface over here connecting it to the networking switch, but it also has some logical interfaces, bridge 1 and bridge 2 interface. And in Linux, there are several types of logical interfaces that can be configured. In case of bridge interfaces, this is like putting a network segment inside of a single server, inside of a single operating system, where layer 2 forwarding can be done. Now, it is also possible to assign an IP address to a logical interface, including bridge interfaces. So here we've got IP address B and IP address H for the second interface. Now, these IP addresses can communicate with each other, at least by default. So we would be able to ping one IP address from the other. However, in multi-tenancy scenarios, we would actually require for these bridges and for these IP addresses to be separated. Because, for example, one of the IP addresses might be used to run a service from one customer, and the second IP address might be running service from another customer, and they should not be able to communicate with each other. In case of Linux, there are several ways to achieve this functionality, and what we did here is we used VRFs, so-called VRFs, which stand for Virtual Routing and Forwarding. And basically, creating a VRF is creating additional routing and switching tables. So here we've got bridge 1, which is assigned to VRF 1, and it means that now bridge 1 can only communicate with other interfaces, be it logical or physical, that are also connected to the same VRF. It is no longer able to communicate with interfaces located in global routing table or in other VRFs. Now, the same functionality is also available on most of modern data center switches, where we can assign, for example, a physical interface port 1 to VRF1 and interface port 2 to VRF2. And thanks to that, server 1 and server 2 would also not be able to communicate with each other. So this multi-tenancy can also be provided easily by the networking devices. It is also supported on the VXLAN tunnels. If we use different virtual network identifiers, then the network segments in the overlay topology that we create are also separated from each other, at least by default. So this is okay for us. Now, the only thing that is left is to also have EVPN sustain this separation, sustain this multi-tenancy. And it does support it. And in order to do that, it uses so-called root targets. This is a feature of BGP protocol. And basically, it is adding some extra values to the MAC and IP information that is being advertised by the EVPN protocol. So, for example, here we've got, again, server 3 with bridge 1, and this bridge 1 interface has MAC address B associated with it. This MAC address will be put by the operating system in the switching table for VRF1, and EVPN will notice, all right, I've got a new MAC address that I need to advertise. However, it will be advertised with the root target value that is associated with this VRF1 routing table and switching table. So this information will be sent to leaf1 switch, and leaf1 will take a look at the advertisement and also make sure to note the root target, because this will determine to which switching table it will put the information into. Here we see that MAC address B is being entered into switching table for VRF1, and the destination is VXLAN interface located leading to server 3. All right, and thanks to this configuration, we achieve a topology, we achieve an environment where we have server 1 with IP address configured on physical interface, which can communicate at layer 2 and layer 3 with IP address that is set up, that is configured on some logical interface on server 3. Another server 2, being able to communicate with an IP address configured on second interface on server 3. However, these interfaces are separated from each other using VRFs, so we've got this multi-tenancy sustained here as well. One last thing to notice on this slide is that leaf2 does not take part in the VXLAN tunneling and doesn't need to run EVPN. And in truth, if most of our servers would run FRR, then we wouldn't need many, or we wouldn't need even at all, networking devices that support EVPN or VXLANs. Depending on the scenario. So it can be quite, it can be something that can decrease the costs of the solution if we are running EVPN and VXLANs in software. Okay, so you might be thinking that this EVPN must be very complicated, that creating these VRFs on Linux is also probably hard work. But in truth, when you get the hang of it, it is not that hard, and it is not many commands in order to configure it. So for example, here we've got a server where we want to create a new bridge interface with some IP address assigned to it. In order to do that, we issue two commands in Linux. We create a new interface with bridge1, with the name bridge1 and the type bridge, network bridge. And we assign an IP address to it. Now, we want to separate this interface from all other IP addresses and interfaces that might be configured on the same server. So we are creating a VRF1 and putting the bridge interface into it. So this is these three commands: create new VRF, enable it, and associate bridge1 interface with VRF1. As the next step, we want to be able to communicate, we want to be able to allow for communication with whatever is connected to bridge1 through the VXLAN tunnel to all the other MAC and IP addresses that are also associated, connected to VNI1. And in the opposite direction, also everything that is coming through VXLAN 1 tunnel to the server will be sent to the bridge1 interface. So in order to do that, we create VXLAN interface with virtual network identifier 1, standard UDP destination port for VXLANs, and we also make sure to specify here that the local endpoint will be at IP address of 10.0.1.11, so the endpoint of VXLAN is at the loopback interface over here. We enable this new interface, and we attach it to the bridge1 logical interface. So this is it when it comes to the configuration of interfaces in Linux. The last thing that we need to do is to enable advertisements using EVPN. Here we assume that we are starting from the place where we left off at the last webinar. So the FRR daemon is up and running, the BGP protocol is enabled, and what we do is we just enable EVPN address family, create configuration for VNI1, where we specify appropriate root targets for our VRF, and then we enable the EVPN advertisements. So in truth, this is quite a few commands, but not a lot. And this kind of configuration, keep in mind that can be simplified and automated using scripting. So it is not that hard to do at all.
Okay, so we have Linux and bridges connected and assigned to the VRF. So now let's move to the virtual machines. We can connect them. There are two ways to do so. Each virtual machine in the Linux most frequently is associated with the TAP interface, the layer 2 interface, and we can create a virtual machine. We can assign the TAP interface using the IP-link set master command and assign that TAP interface to the bridge. That bridge must be already assigned to the VRF, so as soon as the packet leaves the virtual machine, it appears on the TAP interface and then goes to the bridge and then is handled by the Linux and routed accordingly to the routing tables inside that VRF. Or we can create bridges using libvirt, create networks in the libvirt, and then after the libvirt will start, the net will assign those bridges to the virtual VRFs, and then we create virtual machines in the libvirt using libvirt tools and assign them to the libvirt network, and those machines will appear in the VRF automatically. So we can have even DHCP running in the libvirt, and the machines in the network red will have IP assigned. So here we can see that we have a Virch CLI, and we are listing the interfaces of the Alpine Blue, and we can see it is assigned to the Blue network, and we have configured that the Blue bridge is assigned to the separate VRF, so it's separated. So we can have two bridges, two networks in the libvirt, and the virtual machines will be totally isolated from one of each other as long as they will belong to the different VRFs. So this is the virtual machines. Now let's move to the containers. The thing with the Docker or the containers or the Elixir are a little bit more complicated. The container is using host kernel for the network part, so we have to provide a separation there. So we have to have a separate space for the interface, for the routing table, for the layer 2 tables. We can use Linux namespaces for that. Generally, a Linux namespace is a separation of the all network things altogether with the multiple separation on the same operating system. We have global namespace, it always exists, but we can create a new namespace. Having a namespace is only half of the way. We have to put the network interface there. Putting a physical interface give us nothing because we lose that interface from the physical global routing table and we lose connectivity. So we can use VET interface. Those are funny things. Those like virtual pipe. So what comes in at one point comes out on the second point. So we create a VET pair. We move one endpoint to the namespace that is dedicated for that container. The other part, the other endpoint that is left in the global routing table, we assign that to the bridge that is already in the VRF. So as soon as the container in the namespace creates a packet, that packet goes into the VET, appears on the other end of the virtual tube, and the other endpoint is assigned to the bridge, so that packet appears on the bridge and is routed accordingly to the routing tables of the VRF. Now let's move to the Kubernetes. The Kubernetes was the hardest part to adapt, although the concept of the Kubernetes is pretty simple. There are containers connected to the bridges, just like in the previous slide. Soon it became really obvious that the devil lies in the details. So all the pods share the same bridge, the same flat network. None of the existing CNIs supports BGP plus AVPN and VXLAN. Some of them support VXLAN, some of them support BGP. We have found any that supports both of those things. The kubelet must communicate with the pods on each node. So just for example, for the health check. So if the pod is in the dedicated VRF, the kubelet is separated from in the global routing table. There is no communication. The pod has health failed. Also, the subnet for the services, the 10.96.0.0/20, is flat. It cannot be divided. All those things could be solved with writing a new CNI, but that would be a huge amount of work, and it would kind of feel like reinventing the wheel. So let's deal with above problems one by one. For the one flat network, we can use the CNI called Kube Namespace CNI. It's a CoreOS project. It allows us to attach pods to bridges based on the Kubernetes namespace. This is different thing than the Linux namespace, do not mix them up. Since the bridges are already assigned to the VRF, so we have correlation between Kubernetes and the VRF, that part is done. As for the communication between the bridges, between the nodes, that was taken care by the FRR and the BGP and advertisement of using AVPN family, so that part is done as well. For the communication between the kubelet and the pods, we have to use a thing called route leaking. Again, we can use that interface. One interface is assigned in the global routing table, the other is placed in the VRF. We do some static routes, and then we can communicate from the pod with the pod between the global routing table and the pod. As for the last part, for the service network, we can divide that network manually into /24 prefixes, assign each prefix into dedicated namespace, dedicated VRF or the namespace from the Kubernetes point of view, and use that subnet for advertising services. So with that all together, we have working Kubernetes, and we can move to the demo. The demo agenda is divided into 9 parts. First, we'll show and try to explain the topology. Then we'll start creating resources, just like LXC, Kubernetes pod, Kubernetes services, and we'll show that we have connectivity inside each VRF while having no connectivity between VRF. The virtual machines will be already created because they are taking a lot of time to be deployed and configured, so that part was skipped, but this can be done easily using Irsch. Okay, this picture presents the whole topology with all the details. I agree, we all agree it's a little bit of clutter there, so let's break those information into separate slides and deal with them one by one. First, each node was assigned a different role. The first node was designed for the libvirt, so there will be virtual machines running there. The second compute node was designed for containers, the LXC containers. The third, the fifth, and the fourth node were designed for the Kubernetes. The third was for the controller. The others two were for the nodes post deployment. And the last node was a legacy bare metal server, which has no FRR running, and the connectivity will be provided by the LIF1 and LIF2 switches with the proper configuration there. Okay, we mentioned BGP protocol, so let's see how things are connected at this level. Most of the compute nodes, all of them that are running FRR, has 2 external BGP sessions to the LIF switches. Those sessions are used purely for advertisement of the node and advertisement of the switches addresses, and they are being configured automatically as explained in the first webinar. This is just a few lines of the configuration in the FRR. The rest happens automatically on using IPv6 router advertisement, and it was covered in detail last time. The second type of neighborship is internal BGP. All of the pods that are hosting the FRR are connected to the spine switch. The spine switch is acting as a route reflector, and the internal BGP protocol is used for the AVPN family to advertise resources that are placed on each compute node. So we have BGP, we have assignment. Let's move to the VRF. So each compute node has deployed 2 VRFs, the VRF red and the VRF green. We'll go into the details later on. The last compute node is a legacy. There is no VFRR, no VRF configuration there, so it assigned only to a single VRF, and that assignment is done on the switches. That compute node is connected via the bonding interface, and it thinks it's connected to the single switch. So we have a redundancy. Both of those links are active. However, if one switch will fail, the compute 6 will transparently move to the second switch while keeping all the connectivity, a little bit less performance, but still will have communication. Okay, so we have VRF, so let's talk about IP address assignment. On the compute 1 and compute 2, and also on the legacy server, we have stretched one network 10.1.0.0/24. So all resources on the compute node 1 VMs or containers placed in the VRF red will be visible on layer 2 and will give an IP addresses from that address space. The same go for the VRF green. There is 10.2.0.0/24. So VMs placed in VRF green and containers placed there will be given IP addresses from that subnet. On the Kubernetes, we decided to go with the simpler configuration. Each node on the Kubernetes has assigned a different /24 prefix for each node, also for each VRF.
Okay, so let's take a look at how it will work in practice. So in the first demo, in the first scenario that we show here, we've got only virtual machines configured, and they are running on comp1 server. We've got VM red here and VM green in the bottom. There are no LXC containers running, there are no Kubernetes pods running at this time. So let's see on the terminal how it will look. We've got here terminal of comp1 server where the virtual machines are running. So as the first step, let's see what networks are visible for libvirt. So libvirt sees the default network, the green network, and the red network. So we've got the two networks that we are interested in here during this presentation. Next thing that we want to check is the virtual machines that are running on the server, and we indeed see two VMs, Alpine Red and Alpine Green. All right. Next step that we would like to check is where are these virtual machines connected to either the default network, the green network, or the red network. So for the Alpine Red virtual machine, we've got a single interface assigned, and it is connected to the red network. And this is the MAC address that is used by this VM. Okay, and let's just check the second virtual machine connected to the green network, also single interface and a different MAC address. So what we can check now is we can log into these virtual machines. Let's start with Alpine Red, and let's see the IP addresses that are configured on its interfaces. So it's got a single interface that we are interested in, Ethernet 1 with IP address 10.1.0.60. So this is from the range of this VRF Red. Now, there are no containers or no from either LXC or Docker running at this time. However, there is a default gateway configured in both VRF Red and VRF Green. So let's see if we can ping this default gateway. All right, we've got the communication here. This is good. Let's continue with the green virtual machine. Okay, sorry, we're going to log into it. Right now, again, see the IP addresses. This is a different subnetwork. What we are going to check whether or not we've got connectivity to the default gateway in VRF Green. Yes, we do. However, we should not be able to ping the IP address of VM Red. So even though both of these VMs are running on the same servers, they are put in different VRFs. And indeed, they cannot ping each other. Now, the information about these virtual machines, their MAC addresses and their IP addresses, should be automatically advertised by EVPN. EVPN is already configured, it is up and running, and the advertisements should reach all other BGP daemons in our data center. So this obviously will include second server comp2. So let's take a look at the neighbors, so ARP entries in this scenario for VRF Red on comp2. And we are interested in the IP address of VM Red. Okay, and we've got it. We've got its IP, we've got its MAC address, and we also have information that it has been learned from the external source, in this case, EVPN. All right, this should also be true for the green VRF, but here we are looking for the IP address of VM green. And again, we've got it. It has been advertised by EVPN, and all other EVPN devices in the data center do know about it. All right, and finally, IP root of VRF red, when we actually can see different IP addresses that are already pre-configured and located in this VRF, not only individual IP addresses, but also subnetworks which are advertised by this type 5 EVPN root. Okay. Now, let's continue to the second step, where we create LXC containers on the second server. And we are hoping that we will be able to ping between LXC container red and VM red, and that we are able to ping between VM green and LXC green. But they shouldn't be able to ping between the VRFs. Only within a single VRF, this communication should be possible. So let's jump back to the terminals. And at the beginning, let's make sure that at the start, no LXC containers are running. All right. Now we want to create LXC container in VRF green. There's some configuration that already assigns this new container to appropriate network that is associated with VRF red, and now VRF green for the second container. All right, so they are created. Now we need to start them up. Okay, and they should be running by now. So LXC, LS. We've got two containers running. Let's log into the LXC red and see the IP address. IP address is configured. Sorry, 1 second. A slight technical trouble. Okay. So these are the IP addresses. One more second. Please be patient. Okay, I think we're back.
A little bit issue, but we are back on track.
All right. So this is the LXC red container. It's got IP address automatically assigned using DHCP. The DHCP server is actually running on Comp1 server on libvirt, and we want to check whether or not it is able to communicate with the virtual machine that is running also in VRF red. And this is the truth. It can ping it without a problem. Now, just to make sure, let's see if it can communicate with the green virtual machine. And what we see, that it cannot do that, which is also something that we did expect. Now, one more thing that we can check, that we can show you, is that Comp1 has learned information about these containers. So EVPN advertised information about these new MAC and IP addresses, which we can show in the VRF table, in the routing table for VRF red on Comp1. And here we can see the IP address of the container red, and we can see that it is reachable through address 10.0.0.2, which is the loopback interface on server Comp2. This is the IP address to which the traffic is being tunneled using VXLANs.
Okay, having finished with the containers, let's move to the Kubernetes, and during this part, we'll first create the deployment of the two Nginx. First, let's check if the resources are running. We can see that there are only default pods running on the Kubernetes. Nothing special here. We have some namespaces pre-configured already, the green and the red. Again, those namespaces are a typical namespaces of the Kubernetes, nothing new, nothing special here. And we can use those namespaces to do a deployment. So first, let's create a deployment in the namespace called red. Okay, the deployment has been successful. Let's see if it's true. And we can see that the pods in the namespace thread has been deployed, has been assigned IP addresses from the network that are assigned to the compute 4 and compute 5. We are good. Now let's move to the next part. Let's deal with the namespace green here. Again, you are using the same command, the same deployment, but we're specifying a different Kubernetes namespace. Again, it was successful. And we can see that the pods are running on the compute node 4 and 5. They are given different IP addresses dedicated for the APREF green. So there is a different second octet. So it looks fine at this point. Okay, so we have pods running. Now let's create services. Let's expose the first set of pods in the namespace thread, and let's assign it a static IP address 1096.10.100. As we said before, we divided that subnet 10.96 into separate prefixes, and the 10 on the third octet was given to the namespace red. Okay, the exposure was successful. Let's do the same with the namespace green. Done. Okay, now let's go to the container on the compute node 2 and see if that container can reach the container in green, can reach the service that we exposed previously. Okay, this is okay. It took some time, but we can see that we have communication. We can even have a communication from the pod directly to from the container directly to the pod placed in the namespace green. Hey, see, yes, it was successful. Last, let's check if there was some load balancing on the inside the namespace green, and we can see that the requests were divided mostly equally between two pods that were deployed on the namespace green. And at the last, we can see the direct communication between the container and the pod itself. Okay, so this concludes the Kubernetes part. Now let's move to the bare metal server.
Yes, so the last thing that we want to show you during this demo is that we also can achieve this layer 2 communication from a device that doesn't have any support for VXLANs or EVPNs. So in our server, in our case, a bare metal server, from which we would like to be able to reach at layer 2 the LXC container and the virtual machine, and also to be able to reach the cluster IP address in the red VRF, just like we did in the example before this one. However, at the same time, this bare metal server shouldn't be able to communicate with IP addresses in VRF green, and this is because it is assigned to VRF red on the networking devices. So here the separation and multi-tenancy is provided by the Juniper and Arista switches, which appropriately assign traffic from the bare metal server to VRF red. And this is being done over Bond 0 interface configured on COMP6 server. So let's take a look at the consoles again. And here we've got the console of COMP6. We can see that there is an IP address configured or actually received from DHCP server in the VRF red 10.1.0.200. And what we would like to be able to do is to be able to ping to communicate with the VM red located in the same VRF. So this works without a problem. What also shouldn't work without a problem is communication with Kubernetes pods. So bare metal server to Kubernetes. And it also works as expected. Now, what shouldn't work if we've configured our switches correctly is trying to communicate with the cluster IP located in VRF green. So we'll try to ping it. And we can see that the message that we receive is that the destination net is unreachable. So this subnetwork isn't even located anywhere in the VRF red. It is only reachable in VRF green in this topology. So everything is working as it should. Now let's take also a short look at the configuration of the networking devices that allow for this connectivity. So first off, the leaf one switch, which is Juniper, and some of the interesting commands that we might issue is, for example, show EVPN MAC IP table, where we can see the mapping between IP addresses and the MAC addresses, and these are the addresses learned by using EVPN that are located on different servers in our data center. If someone would be very curious and would like to see all of the information advertised by BGP with EVPN, we can actually show a table that lists all of this information. It might seem messy, however, you can actually see some mappings between the MAC addresses and IP addresses that are being advertised over here. What you can also see are the type 5 routes, where we advertise the whole prefixes, and also we can advertise individual IP addresses of hosts. So all of this information is here for you if you need it for some extra configuration, for some advanced scenarios. And just a short look at the configuration of VRF on the networking device over here on the Juniper. So we've got a routing instance, which is at VRF. We've got some layer 3, the default gateway, attached to this VRF. And we also have this magic value of root target, which allows us to map the advertised information with specific VRF. Okay, so this is on Juniper. Now let's see quickly the same similar information on Arista. So here we can check also the ARP table. What we can also check is the routing table as well for specific VRF. This is the VRF red, where we can see the individual host addresses as well as whole prefixes, whole subnetworks. All right. And also let's take a quick look at the configuration of interface that connects the switch to the server COM6. So it is configured with some EVPN Ethernet segment identifier, and it is transferring traffic on VLAN 20. Now this VLAN 20 has a layer 3 interface, which is again a default gateway, and it is assigned to VRF VNI 10. So this is the red VRF. And finally, let's take a look at the BGP configuration for this VRF, where we will be able to see that it also has the same root target assigned that was also used on the Juniper switch. So as long as these root targets are the same, we've got this separation correctly configured, and we can achieve connectivity for VRF red and make sure that the host will not be able to communicate with VRF green in this topology. Okay. And this actually concludes our demo. So we hope that we've been able to show you how this can work in practice. Now let's talk a little bit about the advantages and maybe some disadvantages of the things that we have shown you today. So hopefully we are able to hopefully we are able to present that we do get this capability of transmitting layer 2 traffic over layer 3 only connections such as IP Fabric. Now we've shown this within a single data center. However, this concept can also be used between data centers over the data center interconnect links. It can also be used to stretch layer 2 connectivity to resources located in public clouds, and maybe also to some servers, edge servers that are located somewhere on the internet in general. So this is something that we'll cover on the next webinar. Now, another thing is the interoperability between hardware and software routing daemons. So we've run EVPN on Juniper and Arista, and they were able to correctly communicate, exchange information with each other. And for example, FRR can be also run on different Linux distributions, such as Red Hat, such as Ubuntu, and others as well. So we do not depend on a single supplier from either software or hardware, and it is perfectly okay to have multiple vendors, devices, and solutions from multiple vendors in our data center. What we also shown on the presentation on the demo is that we then can interconnect different kinds of resources. So BMSs, network appliances such as firewalls, logical interfaces on Linux, virtual machines, containers, all can communicate at layer 2. And this can be quite useful when it comes to scenarios when we need to migrate some application from one platform to another. So for example, from bare metal servers to virtual machines, especially if it is required for this layer 2 connectivity to be available there during the migration. Also, it actually enables us to have a heterogeneous data center. So we might have a data center where we are using VMs for one type of applications, we are using bare metal servers for another services, and we can actually have applications that have clusters that are running, that some of part of the cluster might be running on a VM, and another part of the cluster might be running on containers, which might lead to higher uptime of such an application. EVPN also supports some extra built-in mechanisms, and it is important to know that the EVPN standard is still being extended. So there are new drafts being written, new functionalities might arrive in future, and this is quite a future-proof solution because of that. The EVPN is not going away. It actually seems that it is here to stay with us for many years to come. All right, and the last point that we wanted to make, we've already mentioned it, if we've got FRR running on most of our servers, then we do not need many switches that also support EVPN or VXLANs. Okay, and now for a few disadvantages. First off, this is a solution where advanced configuration might require good networking knowledge. Obviously, this configuration can be simplified through scripts. We could use some playbooks. We could use some external management solution that does the EVPN configuration for us. But the truth is that sometimes you do need some extra knowledge in order to configure it appropriately in the best practice manner. Now, EVPN is relatively new, at least compared to protocols such as OSPF or ISIS. However, it is stable. It has a few years behind its back. You might expect some minor bugs on some implementation, but nothing major. All right, and if we are using VXLAN for tunneling traffic over layer 3, then we should expect slightly lower throughput. This is because we've got some extra headers, extra UDP and VXLAN headers in which we encapsulate layer 2 frames. So it means that the throughput will be a little bit lower. In case of large frames, it might be up to 3% lower, a little bit over 3%. However, if we use jumbo frames, where the maximum transmission unit of a frame is 9,000 bytes, then in this case, this effect is really minimized. And it is also visible for large packets. In case of small ones, it isn't really a problem at all. Another thing for VXLAN tunnels is extra CPU utilization. The servers need to use CPU cycles in order to encapsulate the layer 2 frames inside of VXLAN headers. Now, this can be visible in case of small packets, where there is a large number of small packets. However, this effect can again be minimized if we are using network interface cards which support hardware VXLAN offloading. And in this case, this CPU utilization will be negligible.
Okay, so we are slowly coming to the finish of this presentation, but first let's talk about the problems that we have encountered. There were quite a few of them. On the Juniper, we discovered that each EVPN node that is sending layer 3 traffic towards the Juniper switch must also advertise at least one unique type 5 row itself. It doesn't have to be the row that is the same as the packet that is sending. However, it must be some kind of row. It's a bug. It's already known. There is a PR for it as well. On the virtual Arista the MTU has to be increased for the FWD interface and VX interface. Those interfaces are hidden from the configuration, so we have to switch to the shell and manually do IP link set MTU command to increase the MTU to allow jumbo frame processing or even 1500 packets processing. To use that interface for the route leaking, as described in the Kubernetes scenario, we have to change route table priorities, and we have to move the local routing table that consists from the local interfaces just behind the routing tables of the VRF, as shown on the CLI output before. So this route table has to be moved at least here to be able to do a route leaking. This configuration is default from the Ubuntu, so it has to be changed via the script after the system has been boot up. Another thing that we discovered is that due to ICMP load balancing between Kubernetes node and the fact that IP tables that are used by kubeproxy are stateful, the parameter masquerade all has to be enabled on kubeproxy to have services working properly. Another thing that is discovered is that the reverse packet filtering has to be disabled on compute node 2 or the SVI IP address has to be enabled just to the HCP to be working. When we come to the details, this is understandable and it is easy to explain. However, we have to discover that there is some case of asymmetric routing that is causing packets to be dropped. Bridge harpening has to be enabled on layer 3 bridges on Kubernetes node. Again, this is required for cluster IP load balancing. Without it, the packet could be dropped. And last but not least, a few issues were discovered inside the FRR daemon. However, the response from the FRR team was prompt using Slack channel, and the fix came quite often or most of the time within 48 hours. So they are doing a great job here. Okay, let's summarize what we achieved during this presentation. We have shown that the Ethernet VPN is a great tool for layer 2, also layer 3 connectivity. We can create a flexible deployment when everything can talk to each other. So we can have pods, containers, virtual machines, bare metals, all connected via a single layer 2 or multiple layer 3 networks inside one VRF and isolation between VRFs. This solution is priceless. We're doing migration from bare metal to VMs while keeping them in the same network. It gives us a good automation possibilities, so we can do Ansible or Terraform to create configuration and automate the deployment in the further. We have, as said, we have a separation between services, and this solution is very scalable. It is well known that there are deployments of BGP AVPN that reach thousands of nodes and tens of thousands of entities inside that nodes, such as VMs or pods.
Okay, so we are at the end of this presentation, but before we go to the questions and answers, let's just take a look at what you might expect on the third webinar, the last one in the series. So what we'll talk about is the VXLAN routing between two overlay networks, how we can achieve that, how we can communicate between underlay network and overlay networks, so resources that are located behind those VXLAN tunnels. We'll also show how we can interconnect two or maybe even more data centers together, again using VXLANs and the VPN. How can we extend layer 2 connectivity to public clouds such as Amazon? and also to devices located somewhere on the internet, such as edge computing servers or some IoT devices. Also making sure that this communication is secured, that it is properly encrypted. And finally, something that we've called branch office EVPN, where we can extend EVPN and layer 2 connectivity to different offices spread out throughout the globe of our company. Okay, and this is it when it comes to the presentation itself. Now let's go to the questions and answers session. If you have any questions, if something was interesting for you, if you would like to get a little bit more information about some specific part of the presentation, please ask the questions. We'll be here for the next few minutes to answer them directly, if it is possible. And if not, we can also answer them after the webinar has ended and put them in the comments as well, so they are kept there.
So one thing worth mentioning here as well is that all the configuration that was used during this presentation, all the scripts that were used for the deployment are already placed at the GitHub on the link shown here. Feel free to browse through them, use them, or extend them as you wish. So if you have any questions or we can explain something even further, feel free to use YouTube channel to reach us.
Also on this GitHub page, you will find configurations of networking devices as well. We've put the relevant configuration in regards to EVPN there. So if you would like to configure a similar topology and test similar communication in your own lab, then you should be able to quickly adapt the configurations that we posted. And we would like to invite you to do that because it is quite a fun experiment to do it.
Okay.
All right.
So we have a question. Do you have any methods to enable traffic mirroring for pods, VMs in this environment? Well, since it's kernel-based, so at any point we can use pure TCP dump. We can adapt the TCP dump to the VET interface or the bridge or the VRF itself. We can do some IP tables rules that will provide us mirroring, or we can do some kind of mirroring during the S-flow. So there are multiple options, and you can use any of them. So yeah, it's possible and it's easy achievable.
Yeah, and if this traffic is going, for example, between a VM and a bare metal server through a networking switch, the networking switches would also be able, at least many of them, to copy such traffic and do port mirroring, send it to some server that would be able to capture it, for example, again, using TCP dump or some other solution. Okay, any other questions?
Okay, so thank you for watching. If you have any questions, then feel free to use the comments under the YouTube link and we'll check them frequently to provide answer. You can also reach us via the GitHub by creating an issue, and the email is shown on the first slide of this presentation. Feel free to use them as well. Thank you for watching, thank you for being here with us, and we invite you for the third part that will be shown in a few weeks.